For today, we'll be taking a look at some review, specifically on factoring and rational expressions. What we're going to be doing next week is simplifying and trigonometric identities, and we need these kind of basic skills from previous math courses in order to do that easily. So what's going to happen is I'm going to go over two examples of each review topic, and then example 3 is going to be one that the video will pause and you will try. So just note that as we go through each of the next 4 slides. So our first review is factoring using GCF. GCF is typically always a factoring technique that you check for first, and it stands for greatest common factor. So what I want to do is, looking at example 1, 3x cubed plus 12x, I want to identify first, numerically and variable-wise, what's the largest thing that I can take out. So between the 3 and the 12, the GCF here would be 3, and then I have an x, 3x's in the first term, 1x in the second, so I can only take out 1x. Now, I personally write the GCF under each term and then just do the simple division. So we'll get x squared and then plus 4 for that second term. And that's it, GCF 3x times x plus 4, x squared plus 4 rather. For example 2, again, numerically, GCF here would be 14. They both have a y. Oops, not ready to do that yet. They both have 1y, but the second term has 2. But we can take out the smallest exponent you may have learned when you learned GCF the first time. So we can take a 14y out of both terms. Interestingly enough, the first term is the GCF, so that becomes a 1. And then minus 24 divided by 14 is 2. Y squared divided by y is y. So again, the video will pause, try example 3, and then we'll try the next factoring technique. All right, so our next factoring technique is called DOTS, which stands for difference of two squares. And important to note here, difference implies that one of the two terms has to be negative. So all of the examples here are written in the order term 1 minus term 2, but it could be negative. Like the first one could be negative 64 plus x squared. That would still work. You could just reorder it to get it in this typical form. When I'm doing dots, what I typically do is check first, make sure it is truly a difference of 2. And then for squares, I'll make little factor trees and say what times itself gives me x squared. Well, x times x. And what times itself will give me 64? Well, 8 times 8. Important that for both of those, the numbers you're finding or variables are identical. Otherwise, this method does not work. And then dots is always two binomials. Whatever you get from the first factor tree is our first term. Whatever you get from the second is the second term. And then it's always plus in one, minus in the other. It doesn't matter the order, but has to be a plus and a minus. Number 2, we've got x squared minus 4y squared. So factor each of those individually. We get x and x again. This time we'd get 2y and 2y to make 4y squared. So x plus 2y, x minus 2y. And again, you're going to pause the video and try 1 minus 81x squared for your next problem. All right, our next topic is simplifying rational expressions. These are going to take a little bit more work than just factoring because oftentimes they include factoring. So to simplify, and you can see that we've got some multiplication and division here to practice that as well. We're looking for essentially to combine to one fraction and then to look for factors that are both in the top and the bottom to be able to cancel out. That's the concept of simplifying. So if I look at the first one, I have x plus 2 times x minus 1 all over x minus 2. Times x plus 1 over x plus 2. Since this is a multiplication, technically this already could be written as one big fraction. So I could just extend the fraction bar across. And then because when we're multiplying fractions, we just multiply across, I'm just tacking on these two, top and bottom. And now really what I'm looking for is factors that are the same top and bottom. So I see an x plus 2 here and here. And then beyond that, I don't see anything else. So the final answer for this one would just simply be x minus 1 times x plus 1 all over x minus 2. There's nothing else that they have in common. Don't go crazy here. You can't just go like some people will try and do this, like, hey, there's an x here, there's an x here. There, you can't do things like that. You can only cancel out common factors. So when you're factoring, if you do dots or GCF or something like that, they have to be tried and true factors. You can't just go crossing out numbers and variables that are the same. So those x's should still be in this problem. All right, let's take a look at example 2. Note here that this one is division, so I can't just go straight to one big fraction. If you recall the phrase same change flip or keep change flip, whatever you learned, we're going to keep the first fraction the same. But then we're going to change the division to multiplication, and then we flip that other fraction. So the x squared plus x goes up, the x plus 3 goes down. And now note here that both of the numerators are factorable using, of course, the two techniques that we just looked at. So x squared minus 9 is dots, x plus 3, x minus 3. And we still have x plus 1 down here. Big fraction bar at this point because it's multiplication. And then note here, x squared plus x for the second fraction up there. We can take out an x, so x times x plus 1. So we have x plus 1 in the denominator, and the other one was x plus 3. And now let's grab a different color, and we can cancel out things that are the same top and bottom. So I see an x plus 3 both places. I see an x plus 1 both places. So in this case, there's no longer a need for the fraction. I literally can write this. I'm going to put the x first, that GCF, and then x minus 3. Technically, you can write this over 1. You don't need to. More importantly, if this would have been reversed, if the answer would have been, the x times x minus 3 was in the denominator, I have to put a 1 up here. Okay? You don't have to do it in the case of our answer to this one. All right. And example 3 is yours. So factor and reduce as much as possible for number 3. And then we'll take a look at one more review topic. All right, last concept we're going to review is adding and subtracting rational expressions. And this is where we have to find a common denominator because we're going to be adding and subtracting fractions. Rational expressions are just fractional ones that involve variables. So for number 1, note here that we are adding. Important, we'll take a look at example 2 with subtraction, what we have to add on there. But first we want to identify a common denominator. And one of the easiest ways to do that is to just simply use the algorithm BDD, which stands for bottom, diagonal, diagonal. And what that means is that if you want to, you could just simply multiply across the bottom. So that would be x times x minus 3. And then you're going to multiply both diagonals. So I'm going to do 2 times x minus 3. And my other diagonal is x times 3x. And now I just want to clean this up a little bit. So in the top, I can do 2x minus 6. And then x times 3x will get me 3x squared. And then denominator would just be x times x minus 3. Now, we would look for factors to cancel here. I'm going to just tell you that that one is as simplified as it can get. But just to show you that bottom diagonal, diagonal algorithm here for this one. Now, for example 2, there is a subtraction. So the first thing that I would strongly encourage you to do is change that to add the opposite. So make it plus, and then the 3 would get the negative. And then again, we're just going to follow that same ruling. So first we'll multiply across the bottom. So our new denominator is x times x minus 5. And then we'll do the first diagonal. We get 2 times x. Second diagonal would be I'm going to do negative 3 times x minus 5. Now cleaning it up a little bit, we've got 2x, and then it'd be minus 3x plus 15 all over x times x minus 5. And we can combine like terms on the top, so we get negative x plus 15 over x times x minus 5. And again, if there was a way for us to factor and get terms to cancel top and bottom, we would do that. But in this case, the negative x plus 15 is as factored as it's going to get, and the denominator is already factored as well. All right, so example 3, one more time, is all yours. So you're going to simplify and put your answer into the PlayPosit. And then Monday we'll check back in and talk about how to do this with trig identities. Get excited. Good luck.